We provide design and implementation of covariance steering for uncertain contact-rich systems. In this work, we consider robots with contact. In reality, uncertainty always exists. Thus, the robot might not be able to complete its desired task using the open-loop controller. Thus, closed-loop controller is useful. However, planning through contact is already challenging. Also, propagation of uncertainty for contact-rich system can lead to different contact modes with non-Gaussian uncertainty, which makes the design of closed-loop controller extremely challenging. There are several works in this field. Some works achieve closed-loop control for linear complementarity systems with non-stochastic guarantees. We recently proposed open-loop controller for stochastic contact-rich systems, assuming that uncertainty follows Gaussian distribution. Okamoto considered stochastic closed-loop controller for linear dynamical systems with Gaussian uncertainty. Compared to these works, our objective is to design closed-loop controller through contact with stochastic guarantees. Our contributions are as follows. We present formulation of covariance steering for contact-rich systems using our proposed bilevel optimization using particles. It enables the user to formally assess the distribution of the state and contact forces efficiently. As a result, we can achieve stable long-horizon closed-loop motion of the robot with contact. Inspired by cutting plane method in optimization community, we propose important particle algorithm for numerical efficiency. Here, we explain why we need to consider stochastic complementarity system. The dynamics of contact-rich system can be formulated using these equations. Here, we consider uncertain contact parameters and see how the system evolves over time given fixed control inputs with randomly sampled uncertain parameters. As you can see, at t equals 0, the system has no uncertainty. However, since the system has uncertain contact parameters, the system feels stochastic contact forces, which makes the system stochastic with non-Gaussian distribution. Since the system is a hybrid dynamical system, the uncertainty follows non-Gaussian distribution. Also, the system can have multiple different contact modes. Therefore, the traditional chance constraint optimization techniques cannot be directly applied. Thus, we approximate the non-Gaussian distribution using finite dimensional distribution so that we can characterize the distribution of the state and contact forces using particles. Here, we use in total n trajectories of uncertain parameters and the corresponding n trajectories. Over n trajectories, we use the same control inputs and count how many trajectories satisfy the chance constraints. Using this analysis, we can actually formulate chance constraints using particles. In this work, we consider contact-aware feedback controller, which regulates the state and contact forces simultaneously. Using this feedback controller, the optimization problem is formulated in this way. We can use mixed integer programming as reference did. However, we observe that compared to the reference number 1, we have additional bilinear terms. Also, in our test, we observe that we need to have a large number of particles and the computation of mixed integer programming is too demanding. Therefore, we formulate the optimization using nonlinear programming for numerical efficiency based on bilevel optimization. Since we use nonlinear programming, the only constraints we need to carefully consider is this chance constraints using particles, since we cannot use integer variables anymore. Thus, we replace the constraint using bilevel optimization problem. If the ith trajectory satisfies the chance constraints, ti needs to be negative, which makes zi to take 1 to achieve global optimality in lower level optimization problem. Using this logic, we can count how many trajectories satisfy chance constraints without using integer variables. Since we intentionally formulate the lower level optimization problem as LP, we can use the KKT condition to convert the bilevel optimization problem into single-stage nonlinear programming. Here, we show some results for Acrobot with contact. Our contact-aware closed-loop controller could successfully regulate the state and contact state with high user-defined success rate. In contrast, the open-loop controller could only find feasible solution with the lower success rate. This table shows if the framework could find feasible solutions with different controller parameterization with different user-defined success rate. It shows that our contact-aware closed-loop controller is able to achieve regulation for contact-rich system even with high delta, while other two controllers have difficulty finding solution with high delta.